In the previous sessions, we have learned methods to assess rock slope stability and to assess the support requirements if the slope is subject to instability. In this session, we will learn how to design the support for rock slopes and the common methods of rock support and protection used in rock slopes. Rock support for slope is to achieve long-term stability of the slope. Rock support can be generally classified into three categories: reinforcement of rock mass of the slope, structural support to the slope, and the improvement of rock mass of the slope. Reinforcement is to strengthen the rock mass of the slope so that the rock mass can stand and be stable. Structural support is to use retaining structure to support the slope. As we mentioned before, water pressure behind the slope is a negative factor for slope stability. Therefore, providing a drainage to drain the water away in the slope is one of the methods improving the slope. The most common and effective reinforcement method is using steel bolts and anchors that insert into the rock mass, very similar to steel reinforcement bars in concrete, to increase the overall strength and the stability of the rock mass. For slopes cut in fair and good quality rock masses, we learned that the failures are primarily due to the joints in the rock masses. The intact rock materials are usually strong, but rock blocks or wedges can easily slide or top if they are jointed and the joints are with unfavorable orientations. The function of rock bolts is to fix those loose planes, blocks, and wedges to the stable rock mass behind by steel bolts or anchors. The bolts and anchors join the loose rock blocks to the stable rock mass together. This effectively stops sliding and toppling. This is illustrated by the diagram below. For very poor rock mass, such as highly fractured, crushed, highly and completely weathered, or very weak rocks, they behave similar to soils. The strength of those types of rock masses is very low. The failure is general or circular failure. The way to prevent failure and to protect from failure is to build a retaining structure to support the slope, as the one illustrated here. The retaining walls are mostly concrete, but can also be steel structures. Design of such retaining structure can adopt the retaining structure design approach for granular soils, since the very poor rock behaves similar to granular soils. I will not cover the design of retaining wall here. The table here provides general guidelines on slope support design approaches for different rock mass types and the potential failure modes. For slopes excavated in hard rocks of fair to good quality, slope instability is often controlled by joints and fractures. It is termed as structural controlled instability. Those structural controlled instability are typically represented by rock blocks or wedges sliding or losing from the slope. For such type of failure, the common rock support method is to apply systematic bolts or anchors to anchor the potential blocks and the wedges to prevent any movement. For rock slope having large block and the wedge and suffer from potential individual block or wedge sliding, then we can use spot bolting or anchors to anchor down the individual loose blocks and the wedges. If slope contains major faults or bedding planes, and they may have potential failure of plane sliding, again, rock bolts and anchors are the most effective way to anchor the sliding plane and to stop sliding. However, when slope rock masses are very high fractured, poor to very poor quality, and the slope is likely to suffer from circular failure, similar to slopes in soils, then the slope will need to be supported by retaining structures of concrete or steel. We have learned this table earlier in rock mass rating for slope. We can assess the slope stability and provide the support guidelines based on IMR slope. I hope you are familiar with this table and are able to use it to make slope stability assessment and to propose the rock support design. What I want to highlight again is the slope support requirements in the last column. For fair and good rock mass, but with unfavorable joint sets that may cause potential sliding failure, rock bolts are the most effective techniques for stabilizing the slopes. For poor and very poor rock mass, then much extensive supports are needed, including concrete retaining walls and other heavy supports. Apart from using very heavy supports, re-excavation of the slopes, for example, to a gentle slope angle or to undulate the sliding planes, can also be considered. The table here gives more specific guidelines to rock slope support. The general support requirements are the same as in the previous table, but gives more specific support parameters such as bolt spacing, bolt length, and the shotcrete thickness. For slope rock mass rating, IMR slope, greater than 61, no support is needed in general. For slopes with IMR slope rating between 51 and 60, spot bolting is suggested. For spot bolting, potential sliding blocks and wedges need to be identified. Spot bolting is to anchor those blocks and wedges to the solid rock mass behind in the slope. For slope rock mass rating between 41 and 50, systematic bolting and shotcreting are suggested. Standard bolts are to be installed with 1.5 to 2 meter spacing, and the shotcrete is to be spread to 9 to 12 centimeters. For IMR slope between 31 and 40, systematic bolting and shotcreting with a closer spacing of bolts to 1.2 to 1.5 meters, and the shotcreting about 12 to 15 centimeters. IMR slope 21 to 30, systematic bolting of 1 to 1.2 meter spacing, and 15 to 25 cm shotcreting. For poor and very poor slope rock mass rating, lower than 20, intensive systematic bolting with 1 meter spacing together with shotcrete with a very thick shotcrete reinforced with steel mesh or steel fiber. Bolt lengths can be designed according to by taking the longest from one of the following: twice the bolt length, or 3 times the average joint spacing of critical rock bolts, or 10% of the slope height for a high wall slope. For example here, if the designed bolt spacing is 1.5 meter, the average joint spacing of critical block is 0.5 meter, the slope height is 25 meters, then among the 3, the highest value is 3 meters. Then the rock bolt should be designed to 3 meters. We have been mainly using the rock mass rating for slope analysis and the support design, and not using the other rock mass quality method, such as the Q system for slope design. As the Q system has the similar function for rock support design, it can also be used for rock slope support design. However, Q system is primarily used for tunnel support design. We then need to treat slope as a tunnel wall for slope support design. You need to refer the Q design chart on slide 10 to go through the design process. On the horizontal axis, we need to input the Q value to represent the rock mass quality of the slope. Because the walls are generally safer than the roof, we will usually make adjustment for Q value for vertical wall support design in tunnel. We can use the same adjustment for slope as approximation. The general rule for adjustments are: for a original Q value, when Q is greater than 10, then Q wall become 5 times the original Q. When Q is between 0.1 and 10, the Q is equal to 2.5 times the original Q. But when Q is less than 0.1 in a poor rock mass, the Q wall use the Q as for the roof. On the left vertical axis, we need to estimate the actual height for design, and we can use the actual vertical height of the slope. Similar to tunnel support design, different slopes also have different safety requirements. Slopes in residential and urban areas generally demand higher safety factor. As we learned before in the Q system, support design for different safety requirements are reflected by ESR, the excavation support ratio. Using the same concept, ESI for slope are recommended in the table below. For slopes in residential and urban areas, ESI to be used is 0.8. For road, railway, and the tunnel portal, ESI is 1.0. For reservoirs, quarries, and surface mines that generally in remote area and limited human activities, we can use 1.3. Now, having obtained the Q value for the slope wall And having estimated the height of the slope wall and the ESR, we can use the Q design chart to estimate the rock support, similar to the design of rock support for tunnel walls. For example, if the initial rock mass Q value is 5, the slope is 50 meters high, excavated for a road, then the adjusted Q value for the slope wall is 2.5 times 5, becomes 12.5. From the Q chart, we find the intersection of Q of 12.5 and H of 15 is in zone 4. It suggests that the slope will need a systematic bolting with a shotcrete of 4 to 10 cm, say 8 cm. Bolt spacing is about 2 meters and the bolt length is about 4 meters. If we compare the design using IMR slope, Q of 5 is fair quality, which is equivalent to IMR about 41 to 50. The design given by IMR slope is for 40 to 50 is systematic bolting with 1.5 to 2 meter spacing and a 9 to 12 cm shotcrete. And the bolt length is twice the spacing, which is about 3 to 4 meters. The two systems give very similar rock support design. Please note both IMR and the Q systems are estimating the rock mass quality. The approach using IMR and Q are empirical. Nevertheless, they, particularly the IMR slope, provide a systematic and quantitative method allowing us to assess the rock slope stability and to design rock slope support. I showed this flowchart briefly in session 2.2 earlier. It is now perhaps worthwhile for you to go through the flowchart step by step to capture the important stages of rock slope stability assessment and the slope support design. You can see that steps 1 to 6 are very much focused on understanding the geological features and the structures of various discontinuities within the slope, as they are the most important features associated with slope stability and failure. Rock slope safety and stability can be achieved as suggested in step 9 by rock bolts, drainage, and re-excavated the slopes with a lower slope angle. All those methods have been discussed in this session. In the next part of this session, I will illustrate the construction aspect of applying rock support to rock slope. The diagram here shows some of the main rock support and reinforcement techniques adopted by rock slope engineering. As we mentioned again and again, steel bolts, dowels, and anchors are widely used in rock stabilization to pin down rock blocks and the wedges formed by rock joints. Rock bolts are usually a few meters long, often end anchored to give immediate action to the rock mass. Rock anchors are longer and also thicker with steel bars to intersect major geological discontinuities such as faults and bedding planes. They are used to anchoring large sliding planes. Shotcreting is spread concrete directly to the slope face. to apply a layer of concrete. They can be applied from a few centimeters to a few 10 centimeters. Thick concrete shotcreting wall serves as a structure supporting as well to the slope. Concrete can also be used to fill the gap, known as dentil concrete. Sometimes you can hear people mention concrete ribs and beams as a slope support concrete structures. Concrete are also used to build toe walls at the foot of the slope. At the bottom of the diagram, you can also see that the drainage holes drilled into the slope to drain the water from the slope. Let us learn a little more about rock bolts, as this is the single most important rock reinforcement element in rock slope engineering. Rock bolts are typically steel rebars of normally 20 to 25 millimeter in diameter, which takes tensile loads of about 120 to 150 kilonewton. Most of the rock bolts used for rock slope supports are end anchored to provide immediate compression to the rock mass. They are inserted into a pre-drilled holes in the rock mass and then fully grouted to give a long life of serviceability. Steel dewels sometimes are also used for rock slope reinforcement, and they serve very similar function as rock bolts. Bolts are normally about 3 to 5 meters long, and they are designed to have 1 to 2 meters in the solid rock after unstable joints. Design of rock bolt lengths can adopt the analysis of unstable block size or use the rock mass classification system. In other words, we will need to estimate the size of potential unstable rock blocks and the wedges, and then decide the bolt length accordingly. For systematic bolting, we can estimate the block size from joint spacing from geological mapping. Drainage is part of a slope improvement. You can see the drainage holes in the lower part of the slope covered by the shotcrete in the photo here. Drainage can also be provided at the surface to minimize the water seepage into the ground. On the whole, drainage is to reduce the water pressure in the slope that otherwise becoming an additional driving force pushing the slope to fail. Slope re-excavation is another option to be considered to reduce the risk of slope failure. There are possible situations where reducing slope angle can help in reducing the risk of slope failure. One is for very poor rock mass. Having a lower slope angle closer to or lower than the slope rock mass friction angle will lead to safer slope or requires less support. The other case is when a major sliding plane is daylighting on a slope. By reducing the slope angle to be similar or smaller than the sliding plane dip angle, the sliding plane will not be daylighting and the potential of major sliding failure can be avoided. We have learned before that slope orientation in relation to joint and fault orientation is very critical in managing plane and wedge sliding failure. Therefore, optimizing slope orientation excavated can also result in better safety and stability of the slopes. Slope support measures are to stabilize the slope and to prevent the slope from failure. Slope protection measures are to protect people and the structure below the slope from slope failure. Those protection elements ranging from nets on the slope face, ditches at the foot of the slope, fences, and the roof structures over the roads. Mostly, steel wire mesh nets are used to cover the rock slope to protect rock blocks and from falling. Steel nets are anchored by rock bolts. Toe ditching is used to trap the falling rocks at the foot of the slope, sometimes helped by toe fence and a toe wall. Fences can be erected at the toe or on the slope to protect people from falling rocks. For roads building on slopes, in order to protect the road from falling rocks, the roads can be covered by a concrete or steel roof structure. The roof structure needs to be designed and constructed to stand the impact from the falling rock blocks. The photo here is in fact an example of an engineered slope in Singapore. I was responsible for the slope stability assessment and the slope support design. Due to space requirement, this hillside was cut to form a subvertical slope. On the top of the slope, a number of 12-story high-rise residential buildings were constructed, with the closest distance about 10 meters from the edge of the slope. The slope is between 10 to 50 meters high. The rock mass forming the slope is highly fractured and partially weathered granite. Assessments were performed using several methods, including mapping, hemisphere projection, and slope macerating. Slope support design was proposed based on slope rock macerating, in consideration with site accessibility, slope geometry, and work schedule. At the end, the slope was supported by steel rebar dewell, steel mesh, wire mesh, and 15 centimeter shotcrete. Drainage holes were drilled at the lower part of the slope. While we are learning to design slope support, we also must recognize that in some cases and situations, with large-scale sliding, we will not be able to prevent failure. For example, large-scale landsliding after earthquake, as we've seen in the introduction, or the case on this photo, a large wedge fell in a quarry in Hong Kong. We can perhaps sense the size of this wedge, as you can see the tiny trucks and the rock breakers, as well as the double-story offices in the background. This large wedge was formed by two intersecting disclivities and the rock slope. The wedge slides down along the two major discontinuities. For such specific case, specific studies need to be carried out to assess the stability of the wedge, to consider the support of the wedge, and to prepare risk mitigation plan when failure occurs. Thank you for attending this session, and goodbye.